the recording. We're speaking about Brønsted bases and Brønsted acid and bases. And the conjugate here means that this acid and this base, they are conjugate to each other, or connected to each other, and what is not the acid is the rest of the acid, the conjugate base. Of course, you can also reverse the reasoning and start to speak about the base, and then there will be a conjugate acid. There is a we speak about acid-base pairs. It's the same nomenclature. Then also connected to acid base here is a lot of equilibrium calculations and such things, and equilibrium constants. And so a typical equilibrium constant is say the product of everything in the right hand side divided by the product of everything in the left hand side. Do you agree with my nomenclature here? Hello?
Yes.
Yeah, yeah.
Mm-hmm.
If we speak about an acid, then it's easy to put a small subscript here, an A for acid maybe, or if we speak about a base, then we put sometimes a B, or if it's neither acid nor base, then it could be without any subscript, or if it deals with water, then a subscript indicating that. So this doesn't mean that there are separate different equilibrium constants. Of course, they're separate in some sense, but it's the same definition of the equilibrium constant. Sometimes you take the you don't report the actual equilibrium constant, but you report the logarithm or the negative logarithm of it, and this is indicated with the letter P here. So a typical Brønsted acid is something that reacts with water, or in a short form, we can say that it donates the hydrogen to the environment. And a typical Brønsted base is something that reacts with water. There is not a simple short type of representation as with the acids for the bases, but we need to, I think, include the water, that the base accepts an hydrogen and forms a corresponding conjugate acid, and the rest of the water is left as a hydroxide ion. Well, that is the thing that gives the base its name. I mean, why is a base B minus called a base? Because when we put it in water or in some solution, it will create a basic reaction, or it will attract hydrogen ions from the solvent. This later is less easy to see formally, but you can detect one of the products that are formed here. So, strong or weak, we had a category, two categories, and that has to do with the the value of the equilibrium constant. Now let's see. Sorry, my pen. The value of the equilibrium constant for this very equilibrium, it's sometimes in my program it's difficult to write these double arrows, so it's usually only a right arrow. A strong acid is something that if HA should be classified as a strong acid, then it means that this is large. Essentially everything is dissociated. And then you can claim that the amount of acid that you put in some system will produce the same amount of hydrogen ions. So even if the say the definition of the pH is the minus logarithm of the hydrogen ion activity, we can say that the activity and concentrations, they are similar in the sense that the activity is the value of the concentration. Then if this is what we want, then we could actually replace the formal correct definition of pH with the concentration of the strong acid. But this assumes that this strong acid is, in the book it says, completely dissociated. I hesitate to say that. I think one should say it's not, perhaps not completely driven to the right, but only partly. But in general, for all acids, there is a tendency for the reunion of the hydrogen ion and the conjugate base. But for a strong acid, it's very, very strongly shifted to the right. So with that, now let's see. With that, one can use this pH equals the minus logarithm of the acid concentration. This is a risk. It's valid for strong acid, but not for all acids. So in...
Yes. I have a question. I didn't really catch it. What's the difference in the brackets here when you?
Yeah. The difference of the brackets, they are. I take a whiteboard here now. Let's see, pen on. Say that you should have if we have the hydrogen ion concentration, that is. Say moles per cubic decimeter or something like that, and a value. But then pH, if we define that as the logarithm of the hydrogen ion concentration, what is the unit of pH? This is actually a problem. Because it would be logarithmic moles per logarithmic cubic decimeter. And what is a logarithmic mole? I don't know. So if we interpret this as only the value of the concentration, that if we don't care about this problem, then we can use this definition. But the formal way to get rid of it is to introduce something called the activity. Activity, yes. So, for example, it's valid. The definition is valid for any ion and anything in a solution. It's the concentration of the ion compared to some standard concentration. standard concentration, we can speak about it as indicate it with the superscript 0 here, or sometimes you see the 0 with a line through, just to use a very, very special 0 symbol then. So suppose we had 4 moles per, if the concentration is 4 moles per cubic decimeter of hydrogen ions, for example. Sorry, we should of course write it below here since we can. Then or why make such a strange value? Say it's 1 moles per cubic decimeter. Then what is the activity of this solution? Well, it is 1 moles per cubic decimeter. And what is the standard activity? That is defined for all ions in the solution as a solution with the concentration of 1 moles per cubic decimeter. So in this case, the activity would be 1/1 is of course 1, but the interesting thing is that the moles per cubic decimeter appears both in the numerator and denominator, so it's just a number. It's no unit, or has the units of numbers. I don't know if one speaks about that. With another, say it's 0.1 moles per cubic decimeter, then we use 0.1, but we still use 1. So if the concentration is 0.1 moles per cubic decimeter, that means that the activity of that concentrations is 0.1. So it's just the value of the concentration, so to say. And this concept, we speak about the activity of ion solutions, for example. We can also speak about activities of solid phases and liquid phases. For example, suppose we have an acid that should react with water, and make this one. And we have some equilibrium constant here. So the equilibrium constant is the right-hand side. It's the A minus times the H3O plus divided by the left hand. It's the HA times the this water. Yeah, okay. So what is this K value? It has some value. And since it's an equilibrium constant, it is a constant value. It's the same value all the time. Excuse me. And how about this water down here? In some chemistry disciplines, one can put in a concentration in dilute solutions as 55 moles per cubic decimeter. But that is perhaps a problem, because if we take 2 of them, then sorry. If I skip this water in the expression here, and instead write this as a hydrogen ion. Isn't this the same expression? So instead of the H3O plus, we type the H plus. But what about this value? It's a problem actually. But if this means the activity, then it's not a problem. Because what is the activity? What is the concentration? Sorry. What is the concentration of water in a dilute solution compared to the standard concentration of standard water? Well, it is of course the same, so that will create a unit here. So whenever water or solvents occur in equilibrium expressions, if we put water, then we should have an oxonium ion here. Then, of course, it's not wrong to write up the water, but actually the value here, as long as we use activities, is a unit. And that's good, because then the constant, the expression for the equilibrium constant will be independent on whether we introduce a solvent and describe it as a hydrogen ion migration to the solvent or not. If we just skip the solvent and just tell it's a hydrogen ion. So these units in equilibrium expressions, the reason they occur is because of the definition of the activity. We can get back to more examples concerning activities. Activities is, and here in my graph here, I used some other type of bracket. I don't want to have the bracket that is used solely for indicating concentrations. But for example, this curly bracket, I don't know what they're called in English, is quite a common way to indicate activities.
Thank you very much.
Yeah. So sorry for me getting a bit lengthy. Well, in general, if we don't know if an acid is a strong acid or if it's a weak acid, then we should actually just assume that it is more or less driven this equilibrium to the right. If it's a long, very much shifted to the right, then it's a strong acid. And if it's not so much shifted to the right, then it's a weak acid. So we can always define the equilibrium constant as the activities of the right-hand side divided by the activities of the left hand. And in practice, I mean, it's very, very common to write it up as with the concentration parentheses. But and it's all, unfortunately, it is also common to give units to this equilibrium constants, but that is more or less only a way to well, construct exam question or something like that, and that shouldn't be any units to equilibrium constants, none of them. And it's not with the definition of the in terms of activities. So a typical acid that is treated in water here, this is acetic acid. Now let's see, pen on. Oh, sorry, pen on. So this is acetic acid. Say that I have a beaker with sorry. acetic acid, aqueous. And then I put in some hydroxide ion solution into that, maybe dropwise or something like that, and that is called a titration. So we start here with the solution with in principle only the acid, and then when we add this hydrogen ions solution, then the solution will be less and less acid, and the pH value will increase. And after a while, we come to the equilibrium point, or maybe this is the equilibrium point, where the the pH of the solution increases very, very steeply and very fast. That means that the amount of hydroxide ions, sort of the amount of hydroxide ions which is equal to the volume of the hydroxide ions times the concentration of the same ions. That is equal to the amount of acid from the beginning. And that is the reason why we call this equality point of equality, or point of equivalence. What is equivalent? It is the amount of hydrogen ions or amount of, well, they derive from the acid. That is equivalent to the amount of hydroxide ions that we added at this very point. And we detect this point by seeing that as long as there are any acid left in the solution, then the solution is more or less acidous. But when the acid is less and less, and when the solution is empty of acid molecules, then the pH will increase very steeply, and we will reach the equilibrium point, or equivalence point. Not it's equilibrium in every point, because if we look at one point, then there are some reactions between the molecules in the solution, and of course on a microscopic level it's not equilibrium and it's not static. It's very dynamic, probably, in a aqueous solution with an acids and bases occurring, but there is no net change in properties, for example, pH of the solution. So equilibrium is equilibrium at every point. But then this is an equivalence point. Where what is, and the equivalent thing is that the amount of hydroxide ions is equivalent to the amount of acid that we added from the beginning. Now this was a bit messy now, so and in addition to this equivalence point, there is also a half way point or something like that. Half titration point, and if you look at the pH value of the curve at the half point, so then you can say that the pH equals the pKa value for the acid that you start with, and here you see that we have pH. I also added another axis a pOH axis. This is much less usual to find in books about aqueous chemistry and such things. But in a way, since there are in water, there is a lot of hydrogen ions, but as well as a lot of hydroxide ions. So why not speak about pOH and pH? There is a simple rule that relates these two to each other. It's 14. This is the something called the autoprotolysis constant of water. We get back to that. Looking at the titration curve as an acid that is titrated, and here what's rest in the acid system is no more any acid but only the conjugate base. So if you would speak about the base, is it what kind of effect does it have? Well, it's a conjugate base to acid HA, but it's also basic since we call it a base. So then it's perhaps reasonable to speak about pOH. And because of this relation, the pH axis is pointing upwards. If it is pointing upwards, then the pOH, the positive direction of pOH is pointing downwards. And the corresponding values, for example, 4 and 10, 8 and 6, they are chosen just because we set this axis first because we measure pH when I did this titration, and then we calculate the corresponding pOH values. Looking at this, suppose we would have started with this base and titrated instead of hydroxide ion, we could have titrated with, say, hydrogen ions in hydrochloric acid or something like that. Then we would have reversed the titration curve. And then it's reasonable if we want to characterize this base in some respect, we could define a pKb. It's the pOH at the halfway point. This seems to be a simple relation, and it is actually quite a simple relation. I'm not sure, this graph is not from the book, but I think these relations are given in the book, as stated. But I think you need a graphical visualization, otherwise they may not mean anything. No, let's see, let me check time. 9:44, a couple of minutes more. Can you stand that?
Yeah, sure.
Yeah. And then any acid, any acid that is reacting with water and forms a conjugate base, or any base that reacts with water and forms a conjugate acid. I mean, you see that this is more or less just by swapping right hand and left hand side. Well, and we change this hydrogen ion, oxonium ions to hydroxide ions here. But we can define, in principle, the acidity constant as the right hand divided by the left hand side in the formula that represents the reaction of the acid with water. So it's A minus times oxonium divided by HA and H2O. And since this H2O is in principle, if it's a dilute solution, we can just get rid of it and replace it by a unit. This expression is the correct expression for the acidity constant. But it's very often represented as the concentration, the codes of concentrations, because the activity of A minus is equal to the value of the concentration of the A minus, and the activity of oxonium is equal to the concentration of the oxonium, the value of the concentration. But here one could fall into a trap that seeing that if this is a concentration and this is a concentration in denominator here, so then we get the unit of the equilibrium constant. But don't fall into that trap. Even if there is an examiner that says it should have a concentration, that's you should argue against the use of concentrations or units in general to equilibrium constants, because they are formally they are defined as relations between activities. But of course, I mean, you can define it. And in secondary school, for example, when you meet these equilibrium constants, if you meet it, then this is perhaps an exercise that one practices to see that there should be different units of the equilibrium constants. But we skip the units from now on. If we have this expression for Ka and Kb, now let's see, do we have another picture here that, no, we didn't. Let me take another whiteboard. And of course, you don't remember what was written there, but if we take this, the product of these two. Now let's see. The previous one was A minus H3O plus divided by HA, that is Ka times, and Kb is now let's see, so I don't mislead you. It's this is the expression for Kb, and we can see that what is this now? HA occurs in both numerator and denominator. A minus occurs in both. So this is just H3O plus times OH minus. And what is this? Well, we can actually, if we take the water molecule and let it react with another water molecule and exchange sort of protons or hydrogen ions with each other, so then we will have H3O plus OH minus. And if we type the equilibrium constant for this, we can call it Kw because it deals with water. So then it's the H3O plus and OH minus divided by the H2O. This is 2 times that one and that one, so we should either have it 2 times or we can indicate that with a square here. But this was unity, so 1 square is perhaps unnecessary to state. So this is just H3O plus and OH minus. This is the same as we have here. So we can take the arrangement that the acidity constant for an acid in water and the base constant for a base, dissociated in water, they are related with this water constant. We call it the auto protolysis constant of water. It has a special value, 10 to the minus 14, at least at 298 kelvins. And in pure water, in water at 298 Kelvin, this is the autoprotolysis constant. At other temperatures, it's not. It's slightly, we can always say it's approximately 10 to the minus 14 if you don't have very high expectations of accuracy. If you allow an order of magnitude or something like that error, then it's okay. It is perhaps not so important an order of magnitude. So this is Kw 10 to the minus 14. If we take the logarithm of these, so then we, or if we just actually take the negative logarithm, then we will have pKa plus pKb equals pKw, or 14. These two versions, they are equivalent. This is very, very similar to the rule that pH plus pOH equals 14. But beware, they are not the same, but they are related, of course. Not the same. I write that because then you can look at the video afterwards and ask yourself, what was he actually speaking about, this crazy guy? Of course, the 14 is the same 14, of course, but pH is not equal to pKa, and pOH is not equal to pKb. But of course, they are related. I mean, some acid will give hydrogen ions, and some base will give hydroxide ions in water. So now let's see. Next page, we have a list of acids and bases. This is my own compilation of acids and bases, and perhaps it's not in total correct, but we can at least the value of the HCl is different in this compilation than in some other compilations. If we take an acid where we agree, hydrofluoric acid, for example, or acetic acid, then they have kind of small Ka values. And instead of speaking that the Ka value is 5 times 10 to the minus 4, quite a long sentence, you can say the pKa is 3.3. This is simpler in a way. And I think the use of these logarithmic entities, it derives from that is simpler to speak about small and large numbers in a logarithmic way. And that was more important for 100 years ago than it is now. But we still use the same nomenclature. Well, it's nothing wrong with that. The acid, if that has a pKa of 3.3, then the conjugate base has a pKb equivalent to 14 minus that one. Actually, this is not, I haven't determined or looked them up from experimental determinations, but are actually just fake these values of pKb, and they are, I think, correct, at least in a decimal or so, because the sum that it should be 14 is quite a good rule, at least at 298 Kelvin in water solution. But when we go away from 298 Kelvin temperature, then it's not valid anymore. So this should be stated at 298 Kelvin. This is correct. Not otherwise, but otherwise it's approximately correct. You see some, if we take the strong acids, they have very large, now let's see, sorry. The strong acids, they have conjugate bases that are very weak. If these are strong, that means that they have a high ability to donate hydrogen ions to the environment. Then the bases could, of course, not also be strong. They have to be weak by some logic argument, and of course they are also. On the other hand, the weak acids, we can take, well, here are some weak acids. They are very weak, and we actually include water also. But the bases, they are quite strong. They have, well, this is not a high value, so we skip this one. But the last two, they are very, very weak as acids, but the corresponding bases, they are quite strong. If you want to point out something, this oxonium ion is the strongest one that you can have in water. It's the biggest Ka that can exist in water because it's related to water, of course, and water is the conjugate base to the oxonium ion. It's a very, very weak base. Water, on the other hand, in itself is the related also to hydroxide ions. Hydroxide ion is the strongest base that can occur in water. If you can have a stronger base in water, but then as long as you have water in surplus and more water than that base, so then it will transform to hydroxide ions. For example, I don't have any examples of stronger bases here, but I have examples of stronger acids. But in principle, they can't exist in water because they are so strong acids, so they will donate the hydrogen ions to water molecules and form essentially only the conjugate bases. And a corresponding reasoning and argument would be valid also for stronger bases than the hydroxide ion. A much stronger base than hydroxide ion is, for example, the oxide ion. So if you would dissolve, now let's see, can we get a whiteboard? Yeah, annotation, yes. If you just formally would dissolve some oxide ion in water, then it would immediately steal a hydrogen entity from a water, and we would get 2 hydroxide ions. So this is just, we can't have oxide ions in water, I guess. But of course you can have it on a whiteboard like this or something like that. But now it's perhaps time for a leg stretch and fill up some coffee cup or something like that. How long time do you need? 5 minutes, 10 minutes?
Maybe 5 is enough. I don't know.
Yeah,
sure.
5 is okay for me. So now 10:02, we see each other in 5 minutes.